So hi everyone, once again, welcome all of you to the PI seminar series dedicated to advancements in scientific machine learning. Today I'd like to introduce all of you as well as to welcome again Professor Ahmed Qureshi, who is joining us from Purdue University, where he is an assistant professor in the Department of Computer Science. Dr. Qureshi is also currently serving as an associate editor for IEEE Transactions on Robotics and IEEE Robotics and Automation Letters. In 2024, he received the Outstanding Associate Editor Award from IEEE Robotics and Automation Letters. At Purdue, Dr. Qureshi directs the Cognitive Robot Autonomy and Learning Lab. His group conducts fundamental and applied research in robot planning and control with aim of deploying robots in natural, dynamic, and human environments. His work addresses problems such as scalable and fast motion planning, active perception, human-in-the-loop robot manipulation, mobile navigation, and dynamic data-driven control. So today, for today's talk, Dr. Qureshi will be giving us an overview on his work on self-supervised physics-informed neural motion planners. And these methods directly learn to solve the partial differential equations for motion planning without relying on the expert data for learning, which is considered to be more computationally expensive. And the talk will also cover about a new metric called the arrival time fields, which can be inferred online to map an unknown environment via exploration. So without wasting much time, I would like to request Dr. Qureshi to take over for the rest of the talk. Thank you.
All right. Thank you, Siddharth, for the introduction. So I would start with today's topic. It is neural PDEs for robot mapping and motion planning. And I know most of people here may not have robotics background. So first I will discuss what is robot motion planning problem. And then we will slowly build toward from classical approaches toward these physics-informed self-supervised robot mapping and motion planning method. So let's start with robot motion planning. So motion planning is a way for an agent to coordinate its motion from one point to another while avoiding collision and also satisfying various constraints that are imposed by the human. For example, if I have this rigid object in this 3D environment and I have to navigate it from one point to another while avoiding collisions, the trajectory would look something like that. Then we can also have this car-like robot that will have to navigate while respecting the non-holonomic dynamics of this car system while avoiding collisions to reach the target, which is indicated as a red orientation of the car. Then we can have this for robot manipulator, where a robot arm needs to navigate an environment and avoid collision while satisfying the constraint. For example, here the constraint is the robot cannot tilt this mug sideways. So it always have to keep it upright while moving from one point to another. Then we can impose additional task constraints that robot have to achieve sequence of sub-goals while navigating the environment so that it can achieve some high-level task. For example, in this video, robot need to build this structure that is shown on the top right of this video. So robot continues generating the motion plan while achieving sequence of sub-goals that will eventually lead to this high-level objective that was given to the robot. And beyond robotics, the field of motion planning has application in computer graphics, where we find a path solution for animated character to exhibit some interpretable behavior. In computational biology, people use these motion planning algorithms to find protein folding paths that can lead to some drug discovery applications. Mathematically, this problem looks like this. We have some objective function that this path should optimize. This objective function is denoted as J, and this trajectory should have minimum cost with respect to this function J, and this trajectory should start from some initial state and terminate at some goal state. And on top of this trajectory, as I said, we can impose some task constraint, kinematic constraint, dynamic constraint. And so let's discuss them one by one. So let's say I have this problem of finding a trajectory that starts from some start state and ends at some goal configuration. So this set of cost function will introduce some abstract forbidden space and some feasible space. So we want to design algorithms that can explore this feasible space and find a trajectory connecting my given start and goal. And like I said, it has application in like robot collision avoidance. For example, here robot is moving this object from one point to another while avoiding collision with all the obstacles. And the timer you see here indicates that we are interested in methods that are computationally efficient, that does not take extreme amount of time to find these path solutions, because these spaces like forbidden space, feasible space in high dimensional robot space is huge, and finding a solution there is computationally expensive. Then on top of this trajectory, I can also impose task constraint, like robot need to achieve some intermediate sub goals. For example, if robot need to finish some sub goal A and B, then the trajectory would look something like this. And this is a depiction like the yellow robot need to reach this yellow banana object. Now it is achieving these sub goals, moving this blue object out of the way, and now it has the path available to retrieve this object from the confined environment. Now, if I impose these kinematic constraints, these are function of robot configurations, or you can think of them as something that limits robot degree of freedom, and they introduce this thin manifold inside robot feasible space. And now for the same start and goal, your previous trajectory won't be feasible, so you need to find a new trajectory in this confined space. And these kind of problems appear in a variety of scenarios. Whenever your robot is interacting with your real environment, we will have this kinematic constraint. Here is an example. In this example, this robot need to open this door and then pick up that mug and move it without tilting from one point to another. And the constraints that are limiting robot motion is now this door hinge is controlling the robot motion, because robot is now in contact with this door. It cannot just move freely. It needs to respect the physics of this door system. Now, when moving this object from one point to another, this robot needs to keep it upright so that the fluid inside this cup is not spilled over. And beyond just this example, they appear in other scenarios. For example, when robot is walking, we need to keep the robot stable. So that stability constraint is another kinematic constraint. Similarly, when a robot is doing tool manipulation for assembly tasks, like all these tool orientation and the way, for example, if you think of screwdriver, all of them are imposing some kinematic constraint on the robot motion. And when we have this kinematic constraint, I have this lower dimensional manifold in which I need to find the path solution. Lastly, we can have dynamical constraint, which control the force that robot apply onto the environment when interacting with it. It can control robot speed, or if it is a robot manipulator, it could control the contact force that robot is using to interact with the environment. In today's talk, I will focus on the simple geometric problem as well as the kinematic constraint. But before I go there, I want to highlight like this mathematical set of equations is the representation of my lab. In my lab, we are interested in solving all of these kind of problems under different constraints, and we are interested in finding solutions that are computationally efficient to obtain and also computationally efficient to execute. So let's get deeper into these set of equations. We will not consider symbolic constraint or task constraint, and as well as dynamical constraints. So this problem of motion planning was introduced in 1983 with these three set of papers, where these authors asked a simple question: how we can move piano in this home environment from one point to another. This is famously known as piano movers problem, at least in robot motion planning community. And they asked this question and formalized this problem, like this problem is hard and it is computationally expensive to solve this problem. And since then, many algorithms have been proposed to solve this problem. Here is like a brief taxonomy of like set of algorithms that were available in the past. We had some control-based approaches that provide some that studies control theory to propose solutions to these problems. We had this discrete search-based method that you may know from your AI class, that we have A star and some of its variant that discretize the space and then find the solution through grid search. Then we also have these optimization-based approaches. They propose some nice numerical optimization techniques to optimize the given cost function to find a trajectory connecting the given start and goal. However, they are prone to some local minima, and because they satisfy the cost function as a soft constraint, not as a hard constraint. And before I move further, these previously I discussed this discrete search methods because they discretize the space. When you go to robot dimension and you have, let's say, higher dimension robot system like robot arm, which could be 6 dimension, 7 dimension, or humanoid robot up to like there exists humanoid robot up to like 30 degree of freedom. In that higher dimensional space, discretization is computationally intractable to perform search on. So that's why people propose these like sampling based methods which randomly sample the robot configuration space and to find the path solution. So I will briefly discuss these sampling based motion planners so that I can highlight their limitations and why we need some new class of methods. So let's discuss these sampling based methods. So these methods, as their name suggests, they randomly sample feasible points from your robot configuration space. And once you have the sample, they find the nearest node in the tree and then connect those two through some steering function. And they keep randomly exploring the space until one node hits the goal configuration and is connectable with your tree or graph. And once you have that node connected to your tree, one branch of the tree is the path solution. As now you can imagine the way these algorithms are working, they are randomly sampling the feasible space and building this tree. And so they have to explore your configuration space before they can converge to some path solution. And when you are in higher dimensional spaces, this exploration and construction of tree is computationally expensive. Therefore, like in my earlier work, I proposed this supervised learning based method that we show that are much faster once trained, and they outperform sampling based planner by a significant margin. And if you see the trend from all these, like from search based method to sampling based and now these supervised learning based method, we are aiming for computational efficiency. Like once we have this method, I should be able to execute it almost real time if possible. So from 2017 till now, the arrow shows you like all the methods that you see, they are aiming for faster and faster algorithms so that once we deploy them on the robot can interact with my environment almost real time. So let's start with these neural motion planner or supervised learning based motion planners. So in my earlier work, like before that, like using these learning-based models for robot motion planning was a bit challenging because we have these complex collision avoidance constraints, and they are very difficult to solve with these learning-based methods. So in my earlier work, I gave a recipe on how you can use deep neural networks to solve this motion planning problem. So we gave a recipe that you need an encoder which takes your environment perception or environment observation from the sensor. It could be LiDAR, it could be RGBD sensor, or whatever sensor your robot is equipped with. It will observe the environment from that sensor, and we need an encoder that can encode it into some latent space. Then the second model that we need is the planning network. So this planning network takes the robot current position or the configuration and the desired goal configuration that robot should reach, and it predicts the next step where robot should go. And we added this condition that in order for these neural networks to work, you need this neural network to be stochastic. The planning network should have some stochasticity in it. Only then it will be able to give you some reasonable performance. And once you have this neural network, they alone are not very good at solving the problem. So you have to stitch them intelligently into some learning-based into some classical path planning algorithms so that you have the best of both worlds, and they both use some like neural network give you some informed sampling, and classical planner leverage those samples to generate a path solution. Given these models, you can train them through imitation learning. When I say imitation learning, basically what I'm saying, you have set of your environments, and in each environment, you can generate multiple start and goal pairs, and you run some classical planner, some sampling-based planner to find multiple trajectories. And once you have multiple path solutions, you can consider them as expert data and then use them to train these neural models. Once they are trained, we stitch it into some planning algorithm to perform the path planning. So we use these neural networks in a bidirectional manner from start to goal, and they alternatively plan toward each other.
So Ahmed, just
Yes.
one question. Can you go back to your previous slide?
Yes.
So the planning networks, do they work in the latent space of the encoder?
Yes.
Okay.
So you have some encoding that will encode your current and target configuration combined with this environment encoding, and then they work in latent space. After they map it into, so you have some transformation here that will map it into C space again.
So you need a kind of a decoder that will map back to the.
Exactly.
Okay. Okay. Yeah, thank you.
So we have these neural networks. You can use them in a bidirectional manner to plan for each other. So we have the start and goal. One network is planning toward the goal, other network is planning toward the start. And if you see, they have decomposed a bigger planning problem into a sequence of sub-problems. And for some of these sub-problems, you may already have the path solution. In this case, we assume if you can connect 2 points with a straight line without collision with this black obstacle, that means you have the solution. But there will be some points which you cannot connect. So here you can see you cannot connect these points. So you run your neural network again on this smaller problem, and you can have a path solution. But worst case, let's say neural network, because it's empirical model that is learned from some data, it is unable to give you a solution. So you can even outsource this problem to some classical sampling-based planner to find the path solution. And this is where it inherits some of the properties of like those sampling-based planners, such as their convergence or ability to find the path solution if one exists. And eventually you will have a final path solution. And when we deployed these models, we had to employ some stochasticity. Our planning network needs to have some stochasticity. In our case, we use dropout even during execution. But if you see other class of models, they are just variant of these versions. They use variational autoencoders or diffusion models somehow to add some stochasticity into the behavior of this planning network. But all of them are following this general recipe of having stochastic planning model. And now it can generate even informed samples for the sampling-based method. You can see it has guided the trees into the region that potentially contains the path solution. And this is like I'm randomly sampling start and goal pair, and you can see within blink of eye, this model can find a path solution for the given problem. Then this is on some car-like robot navigating from one point to another, and you have the solution very quickly. And if you change your imitation data from some constrained planner that is satisfying some kinematic constraint, you can even use this model to solve some kinematic planning problem. For example, here we have this, instead of Euclidean space, you have this spherical space, and you need to find a path solution on this manifold. And you can see if you use this component X, which is neural network based sampling, it is sampling the region that potentially contains the path solution, compared to uniform sampling, where you have to sample the entire space and then you will converge to some path solution. And if you use this neural network sampler and incorporate into your sampling-based method that I first demonstrated at the beginning, you can get much faster performance. Here, this robot needs to throw all these bottles and can into the trash bin. Then open this cabinet from some random initial state to fully open state. And then move these mugs from inside the cabinet without collision and without tilting and place it on top of the tray. So you can think of this as some bartender robot. And now finally, it will move this pitcher into this cabinet without tilting. Now, if you use this sampling-based planner for this entire problem, you can see that they take roughly around 200 seconds, all of them. And if you combine them with this neural sampler, their computation time decreased like significantly. So we demonstrated on Ray robot here. You can see it will move this mug without tilting from one point to another. Okay, so now we have this supervised learning-based method. As I have shown, sampling-based method were taking like around 200 seconds for that problem, or it takes several minutes, compared to like this supervised learning-based method, which takes seconds. However, if you see their data generation time, if I have this supervised learning-based method, their data generation time is from hours to days, because you will have to run those sampling-based planner to find a lot of trajectories and then train neural models on them. So this is not very ideal, because if you are gaining time during execution, but if you accumulate that with the time you took to gather your data and train your model, the advantage is not that significant. So we asked this question, can we have models that can have data generation times of few minutes, and then they are even faster than this supervised learning based method? The answer is yes. We can use neural PDEs to solve these motion planning problems and design some self-supervised methods that can solve these motion planning problems. So the next focus will be on this new class of method, which we call self-supervised motion planners. And that's where we are on the today's agenda. So now you have this problem of solving some physics equation for robot motion planning. So first question was which equation to use. So we used Eikonal PDE. It relates this T here, it is arrival time field. So given your start and goal, X and Y here are some start and goal coordinates. Given your start and goal, this function should predict some arrival time distance. And Eikonal PDE relates it with some speed model. The speed basically says that whenever this configuration is in obstacle space, so these black lines are obstacles, these black rectangles that you see, they are obstacles. So whenever your point is in that obstacle space, the speed of the robot should be 0, because inside obstacle robot cannot move. And whenever you are in free space, the speed can have some constant value or some function of distance to the nearest obstacle. So the speed model is not, do not confuse it with the robot motion speed. It is the terminology used by Eikonal PDE. So this speed is basically some scalar value that this point Y can get, and this depends on the distance to obstacles. And then Eikonal PDE relate the speed function that you defined to the arrival time distance between start and goal. So solution of this equation represents the shortest arrival time from a given start to goal. Classical methods leverage discretization and search to solve this equation. So one of those methods is fast marching method. They solve this Eikonal PDE, but because they rely on discretization, they cannot scale beyond 3-dimensional space. But when we talk about robot motion planning, we are talking about higher dimensional robot configuration space, which could be up to like 100 degree of freedom if you have like complex humanoid robot.
So Ahmed, just to clarify here,
Yes.
X is the start point and Y is the end point, right?
Yes.
And your Laplacian operator is with respect to Y. That means you're taking the physical coordinates
Exactly.
of the space, 2D or 3D space.
Exactly.
Okay.
So, and then this FFM solved this equation through numerical approaches to find this wavefronts that guide the robot from one point to another, from any point to the source point.
Okay. Yeah. That's perfect. Yeah.
Yeah. But because these like numerical approaches, we cannot use it for robot space. They are higher dimensional. So we thought like, how about we use neural network to solve this equation? But then some properties of these equations impose several challenges for using neural network. So first, the main property that imposed challenge was this last one. When you have speed of 0, meaning that your one point of the robot is in the obstacle space, we want the speed to be 0. Then you have this singularity here that 1/0, you have this function that should predict some large number. Other properties of this Eikonal PDE is if you are solving a geometric problem, meaning that you do not have car dynamics involved, then the arrival time distance from your start to goal and from goal to start should be same. Lastly, when you have two same points, robot is standing static, this function should predict 0 distance because robot is not moving. So this is difficult to impose on neural network. Neural network cannot predict something that is infinite, and so it will run into issues whenever your start or goal is in the obstacle space. So we refactorize this Eikonal PDE, and so that it is better suited for neural network. And then we also introduce some training strategies that can better train the neural network to guide them to some better local minima. So let's discuss them one by one. So I will begin with this reformulation of Eikonal PDE. So we said you can redefine this arrival time with this function. What this function is doing, on the numerator, you have some Euclidean distance between your start and goal. On the denominator, you have some function tau, which predicts some value between start and goal. Now I can use the neural network to predict this tau, and I can make this neural network predict this tau equal to 1 whenever I have same start and goal position. So whenever these are same, your denominator will be 1, but numerator will be 0. So it satisfies your synchrony property. And when your one of the configuration is in the obstacle, you can make this neural network predict 0. And then again, this arrival time will have this large value because tau is 0 here. So it satisfies this third property. For the first property, I'm using neural network as a black box structure here. But if you read our paper, anti-field, which was published in iClear 2023, we impose that symmetry through some better design of this neural network so that it satisfies that symmetry property. For now, I will not discuss the symmetric property. You can check it in the paper. I will focus on just this factorized formulation and treat neural network as a black box. So now it is easier to train. I can have neural network that take my start and goal pair, predict this tau, and then I can use this tau to parameterize my factorized Eikonal PDE to predict the travel time. However, we ran into another issue, like when we impose this like collision avoidance constraint, we had to face with these sharp features. If you see near obstacle, there are sharp features, meaning that this Eikonal PDE has multiple solutions. So we added these two terms, one, the derivative of this travel time plus the Laplacian of this travel time, so that we have the neural network that predicts tau, and we use single back propagation or the Hessian to compute this Laplacian. And now I have this semi-linear elliptic PDE that relates my travel time with my speed definition. Now this has unique solution, and I can use this new formulation and do simple differentiation by using this definition of travel time, which is the second equation. And I can plug this into my Eikonal PDE and do the differentiation. I get this equation on the bottom. So I have speed related to the tau predicted by my neural network and its gradients and its Laplacian. So in summary, you give your neural network your start and goal pair, it predicts tau, and you use the gradients and your prediction tau and its gradient parameterize this Eikonal PDE to predict some speed value at the configuration Y. Now I need to train this model. So what I do, I compare this predicted speed with some expert speed defined by the user. And this expert speed model is nothing but distance of a given configuration to the obstacle. We clip it between some min and max value, but what it is essentially saying, your distance of a given point to the nearest obstacle. So higher the distance, you will have some constant maximum speed. The lower the distance, your speed will gradually decrease with respect to your distance value. So now we have this expert speed model, and this is the only data we need. We need a lot of samples, start and goal pairs, and their distance to obstacles. And then we compare them with the predicted speed and train our neural network. So the data that you need is your samples and their distance to obstacles. Compared to previous supervised learning-based method, they were requiring complete trajectories connecting your start and goal, which were very computationally expensive to obtain because you have to run classical planners. Now you can just call some Boolean checker and get the distance of your sampled configurations.
So Ahmed, just one question. So this speed basically is for any location Y, any or any particular. I mean, it's Y is basically the goal, right? But then you can have different goals and you can change Y locations.
So yes, we can have different goals, and also we can change X. We can have different start points. Then you will have to predict speed at X by taking gradient of your neural network with respect to X. So you will have all these like gradients and Laplacian replaced with respect to X.
Okay.
So we have we randomly sample different points in the environment, call them, and randomly form start and goal pairs. Then for start, I compute this predicted speed. Then for goal, I compute this predicted speed. And then for same start and goal, I have this ground truth speed values.
Okay.
Okay. So now let's discuss this progressive training strategy. We basically make neural network first learn a simple problem without obstacles, then start slowly adding obstacles into the environment so that we have better initialization at each time step during the training. So we call it progressive learning because if you see the moment I start adding obstacle, my features start getting very sharp near the obstacle. So we want one neural network to first fit to some simpler problem, then go to a harder problem. And we notice that it leads to really much better performance. And so what we are doing, we have this expert speed model, and we make it function of the scalar parameter alpha that we scale to scale down the obstacle that you see in this environment. So during training, neural network will learn from easier problem, then slowly go toward a harder problem with the hard Boolean avoidance constraint. So with these two approaches, I can train my neural network. We will need a lot of samples for start and goal pairs. This neural network will predict their tau, and then using this tau, it will factorize the Eikonal PDE to predict this speed values at start and goal. Then it will compare it with ground truth speed values at start and goal, and we can define some loss function that minimizes this difference. And again, you will have this progressive learning during this training. So your S star is a function of alpha. So during your training loop, you will keep changing this value of alpha so that you eventually have this hard Boolean avoidance constraint imposed on your model. Once you have trained this, you can use this neural network to do the motion planning. So what basically we do, we take the start and goal, and it goes into neural network. Neural network gives this tau and its gradient. Using tau, you predict this travel time, and using gradients and Laplacian, you predict this predicted speed. And then basically what we do, we follow the gradient of with respect to this travel time from start and goal to guide the robot from one point to another to eventually have this path solution. And the speed here is just acting as a scaling factor. So what we observe that this value is very low near the obstacle, so which allows robot to navigate very slowly when it is in a cluttered scenario, and that really helps in real world experiments. And these gradients are giving direction of motion for the robot to go. So if I have the start and goal, you will see that these gradient of travel time with respect to x give you this arrow, blue arrow, gradient with respect to y gives you this yellow arrow, and eventually in a bidirectional manner, you will have this path solution. So here are some results in a 3D environment. And so first, this anti-field method that you see on the table is something which is not using Laplacian. So it is just solving nonlinear Eikonal PDE, whereas this method on the top, it is solving semi-linear elliptic PDE with Laplacian term in it. And it is also using progressive learning. The third baseline, which is IEF3D, it uses some data, expert data from this FFM planner. So at the beginning, I showed you this FFM solves the Eikonal PDE through numerical optimization and discretization. So this IEF3D method cannot scale beyond 3-dimensional because it relies on the expert, which cannot scale. Then we have the sampling-based planner, RRT star, lazy PRM, RRT connect. There are different versions of sampling-based planners. And in this like home environment where a robot need to navigate from one point to another, you can see over time is just 0.01 second compared to sampling-based planner, which are taking like 3 seconds, 2 seconds, and much higher time. Our success rate with Laplacian and progressive learning is higher than anti-field. And then this IEF3D method, which is supervised learning method, it is slower. And second, I will show you the data generation times are also very high. Then we can even scale this method because this neural based approach, you are not discretizing the space. You can scale it to higher dimensional robot arm, which is navigating these obstacles to go inside these cabinets. And again, you can see the computational time for finding these paths is very low. And we do not have IEF3D here because it cannot scale. We do not have FFM here because that method also cannot scale. Sampling-based methods can scale, but their computational time increased significantly. If you see here in 3D, they were taking 3 seconds. Now, when I move to this 6-dimensional problem, the time increased to 5 seconds. And now if you go toward humanoid robot or like a robot dog, this time will exponentially increase. And these are the data generation times. If you see our method, like in these 3D example, it just took 1 or 2 seconds to gather all those samples and their distance to obstacle. In manipulator, it took like 56 seconds. But for supervised learning based method, you can see it took them like almost 1 day for this environment and then 5 hours for Gibson. This environment took larger time because we had many environments. Gibson, we had just 10 environments, so it's lower time. So now, so far we have discussed just geometric problem. You were avoiding collisions. We did not impose any kinematic constraint or manifold constraint. So what we show that you can even scale them to manifold constraint by just simply changing your speed model. So now you can have, instead of distance to obstacles, you can have some distance to constraint manifold. So the way we define the constraint manifold is so that we can compute this distance. And that is a standard practice in motion planning. So we are not asking any additional information than a standard motion planner. So once you have replaced this data, now your robot configuration will be based, will have the scalar values based on the distance to the manifold. You can even use this to solve these kinematic problems. So here robot is opening the door, moving this mug from one point to another without tilting. Now on the comparison side, for moving cup, you can see our method took like 0.1 second, whereas these sampling-based method C by RRT took like around 6 minutes. And this component X is a supervised learning-based method that I discussed before. It took like 2 seconds. And these are for door opening, and now these are the data generation time. Over method, like because now instead of computing distance to clean, you are computing distance to the manifold. It took like 10 minutes to gather the data. Training time was 4.5 hours, whereas supervised learning based method, it took like 12 hours for data generation and 3 hours for training. Okay. So far we have discussed robot motion planning problem, their solution through sampling-based approaches, their solution through supervised learning-based approaches, and then their solution through self-supervised physics-informed methods that are solving this Eikonal PDE. And then we started asking, like, why we need all these motion planners. And the answer was we need these motion planners because the map we get from the environment is not motion planning friendly. So the mapping of the robot, it generates a map that we use for robot motion planning. And there are different type of maps. There are occupancy map, for example. If you see this fast marching method, we had this occupancy map. The black walls and rectangle shows the occupied area by the obstacles, and this white space shows the free space. And then there are sign distance field method that give you like direct distance to the surfaces for any configuration. And we noticed that the reason we were needing all those like complex motion planning tools such as sampling, optimization, supervised learning, because there is a huge gap between mapping and motion planning. The mapping methods that currently exist, they provide you a feature which necessitate using these computationally expensive tools for motion planning. So we asked, can we have this arrival time as a map of my environment, so that because once I map this arrival time field, I will have these wave fronts in the environment that will directly guide my robot from one point to another. And once we have that arrival time field, my robot can just use the gradients to navigate, and we will have less gap between mapping and motion planning. And our question was, can we get these arrival time field mapping in same amount of time in which people get the sign distance field maps or occupancy maps? So we addressed this challenge, but there were two main challenges when we go that route. One, how can we define this expert speed model? The way my speed model was defined was based on distance to the obstacles. Now I no longer have that because I have an unknown environment for which I need to generate the map. Second problem is how to train neural network online, because I have this Laplacian term here, which is computationally expensive to obtain, and I have to deal with catastrophic forgetting problem of neural network. And if you are mapping the environment, the way it is solved, your robot explores the environment, take the local perception of the environment, and then build the map of the environment. So we resolve these problems one by one. First, to define the speed model, we notice that we do not need really precise speed model. Even some approximate version of it works fine for this neural network. So if your robot is equipped with some depth sensor, which gives rays to the nearest surfaces, and you can use these rays to define your speed model. So along each ray, you can have multiple samples that robot can take in your environment. Then for each sample, you have the approximate distance to the nearest surface. So you can use this data to define your expert speed model. So your robot provides this depth perception, and from that depth perception, you approximate some expert speed based on that just local perception. Second, how to train this neural network efficiently. So we asked like why we really needed Laplacian. The reason we added this Laplacian because we had very sharp features near obstacles that was leading to multiple solutions. So we wanted to arrive at unique solution. And when we dig further, we noticed that this problem is becoming more severe because of the way we factorized our equation. This term travel time, because it is a function of on the numerator you have distance, on the denominator you have tau. When this tau is very small, because near obstacle, I make this tau to be 0. When this tau is very small, this value escalates very quickly. So we have a very sharp gradient there. So we need to replace this formulation with some more flattened reformulation of Eikonal PDE. So what we did, we replaced this formulation with this function. If you plot these two functions, you will see that the second with this log square of this predicted tau, it has like more smooth features and smooth profile when this tau is closer to 0. And when we use this, we notice that we do no longer need Laplacian, and our previous formulation can work fine. And now I have this pipeline where my robot sees the local perception of the environment. From this local perception, I sample multiple start and goal based on my depth rays, and I define the ground truth speed model, and then I use my neural networks to predict the tau for the start and goal. And I train them in a similar fashion like my previous method, and it gives me local travel time. And once I have this local travel time, I can use the loss of the PDEs or some exploration strategy to predict the next viewpoint, and I no longer need any motion planner. I can just follow the gradients of these wavefronts to go from one point to another. And here are the results. Like just from the online perception, you can see robot is exploring the environment and building this arrival time field almost in an online manner. So the red shows the explored path, and this blue one shows the path to next viewpoint. And you can see that robot is exploring the environment and building the arrival time field map of your space. And once you have this map, you can basically, you don't need any motion planner. This map has all the features that are required for a bot to navigate from one point to another. So the speed model, if you see this predicted speed, we can compare it with truncated sign distance field, and we show that the error between the ground truth SDF and our truncated SDF is similar to prior work. So there's ISDF planner, which uses similar technique as over, but they map sign distance field in an unknown environment. Connect fusion is similar, NV blocks in another method. They are learning the sign distance field. And the SDF error between over approach and ISDF is like similar. And connect fusion and NV block, connect fusion has high error, NV blocks is much better than other methods. This frame time shows like how much time it takes for my system to train based on one frame information. So over was higher, it was 2 seconds, other methods are lower. And now my lab is further pushing it so that we can bring this frame time to almost real-time mapping. The overall mapping time, because our method take 1 second extra per frame, it accumulates. So over time, overall mapping time is much higher for our method. However, if you think about it, my robot need to do mapping only once. So it's a one-time procedure. Once you have mapped your environment, consider your Roomba robot navigating your home environment again and again for cleaning. Once you have mapped, you can use it again and again, trillion times to go from one. So overall, if you see the advantage these arrival time field mapping are giving in the long run is much higher than these other mapping features like sign distance field. So once you have this map, we show that you can generate motion plans almost real time. It took like 0.01 second to generate the plan. And this is the path length of the generated path and then success rate. And we compare it with some other sampling based methods and some other motion planning method that use sign distance field for motion planning. And you can see if you use sign distance field, you need computationally expensive tool for mapping for motion planning, and that's why the time is like roughly around 1.5 seconds. Whereas if you have these arrival time field maps, you can generate paths very quickly. So here is a demonstration on a real environment. So this robot is equipped with some sensor here. It's a depth sensor. And on right side, you see the local perception. It is getting depth and RGB. And then we are using it in an online manner to generate these maps. And we show that there is another advantage of this arrival time field mapping. So previously the sign distance fields, they were restricted to your three-dimensional environment because these fields are in workspace. So if you have to do planning in robot configuration space, which is high dimensional, you need some sort of mapping from your workspace to your C space. And usually that mapping is very computationally expensive. So we show that these arrival time field maps, because we are using neural network, you can use robot onboard sensors to map, to generate these map in robot configuration space. And once you have those high dimensional C space maps, robot can directly use them to navigate from one point to another. All right, so we are almost done with our agenda for today. So I will now converge toward conclusions. So in conclusion, previously we had these sampling-based methods. Their data generation time was 0. There was no time to obtain those planners, but their inference time was very high. So it took them several minutes to find path solution. Then we have these learning-based planners, supervised learning-based planners. The data generation time is very high, but their inference time is low. And now we have these PDE-based motion planners or mappers that can take few minutes of data to generate, to get a neural model, which can generate path solution in just sub-seconds. So if I have to summarize key features that we aim for in a motion planner, we are basically looking for 3 features. One is training efficiency. I want my neural network or I want my motion planner to be training efficient. It should be obtainable as quickly as possible. Second, I look for inference efficiency. Once I have that motion planner, I should be able to use it as quickly as possible to realize real-time application of my robot. Third, I want my motion planner to be adaptable to complex problems. So it should not be restricted to just three-dimensional problem. It should be scalable to high-dimensional robot problem, high-dimensional humanoid robot, or those kind of systems. Plus, it should be able to handle some hard kinematic and collision avoidance constraints. So if I summarize, the sampling-based motion planners that we discussed, they have training efficiency because there is no data generation cost to obtain them. And they are adaptable to complex like high-dimensional robot system, but they don't have inference efficiency. Their computational time is high. And then we have these optimization-based approaches. Again, they are training efficient. They are they infer path solution very quickly, but because they convert hard constraint into soft constraint, they are not very adaptable to very cluttered or complex environments. Then we had the supervised learning-based methods. They are adaptable. They exhibit inference efficiency, but their training efficiency is very low. And now we have the self-supervised learning-based method. They are in the center of all these features. They are efficient in training. Their data generation time is not high. They're adaptable to high-dimensional problems. They're adaptable to kinematic constraint, and their inference efficiency is also significantly great. And they work much better than the supervised learning-based method or other traditional planners that I discussed. So with this, I will conclude. These are people in my lab, and without them, none of these would have been possible. I would also like to thank my funding agencies. So that would be all. We can switch to questions.
Thank you, Dr. Ahmed, for your, for the wonderful presentation. I think I did learn quite a lot, especially when it comes to the physics informed part, because that's something that I'm currently working on with Professor Jagtap. So a question that I had was regarding solving the Eikonal PDE. So when you're thinking about a constrained environment, so you already have access to the flow field that you're basically essentially like obtaining after solving your Eikonal PDE. But when you're thinking about like a live moving vehicle or maybe a robot across the length of the room where you don't have access to the complete PDE. So is it like you have to solve this at every new updated state of the robot, you have to like solve it, or is it something that you already solve it and feed it to the to the moving robot so that it's more efficient? So I hope I'm able to understand
Yeah.
convey my
So
question.
that's a very good question. So ideally, we should update our data, like we should relabel our data with new speed model, because as my robot explores the environment, my obstacle features are evolving. So previously I thought this is the minimum distance to the of my sample to the surface. Now
Right.
after exploration, that distance will change.
Yes.
In our algorithm, we did not address that,
Okay.
but just to keep the efficiency, because if you're relabeling the data, you're adding to your training time.
Okay. So just to add once again, just to add one more thing. So when you think about supervised learning, the main constraint is the training efficiency. So if the training efficiency of the existing methods is improved, so how effective do you think supervised learning would be compared to your the method that you have right now?
The supervised learning, like I think the only limitation that they will have is the limitation that generally neural network have.
Okay.
Like each neural network has some limitation, like it cannot maybe overfit to more than, let's say, 100 environments.
Okay.
So that's the bottleneck. Like every 100 environment, you need a new model.
Yes. Okay.
And I think both like the supervised learning and self-supervised have this limitation.
Yep.
Given that we can gather data efficiently, then you can train your supervised learning models in similar fashion as we train self-supervised.
I think that makes sense. Thank you for that, Prof. Thank you.
Any other question?
So, hi, Ahmed. Nice talk. Just two questions. First of all, how you're ensuring that your the PD model, the Eikonal model, Eikonal PDE that you are enforcing in the loss function.
I have some students that have to take.
Do you are you plotting the loss function or the error, the residue
Yeah,
loss?
so we do inspect the loss profile, and then after some time it will just hit a plateau, and then we just stop there. And sometimes, like I said, it can lead to incorrect local minima. And there are a lot of things that I did not discuss here, like the solution that I have presented so far, it has some numerical errors. And we further analyze these PDEs, and that work is still under review and in double-blind conference. So I think you know which conference, but there are still a lot of features that we are not satisfying for this Eikonal PDE, and I will give just a brief highlight on that. So the solution of Eikonal PDE is a value function.
Yeah.
Okay. And we are still not considering the Bellman principle of optimality. We are still not making sure that it has that optimal solution or optimal value function. Right now, we are just treating this Eikonal PDE solution as a geodesic distance. Okay. But we are not treating it as a value function. If we treat it as a value function, then it has different properties, loss function change, everything change. And but when we satisfy that, the performance is much better. We hit better local minima, and it leads to better solution. But most of these results that I'm showing, they are just numerical results. We don't have any like concrete guarantees that it will converge.
Okay. So and also your training time. So basically, which part takes the most of the time? The satisfying the PD, the physics informed part, or the
so the training is mainly like it depends on your neural network size. So when we say that we have this learning based motion planner, so we often want these methods to scale to multiple environments. So we don't want this robot to be specific to one environment, then there's no advantage. And second, we also want it to scale to like unseen environment which are within the distribution of my training set. Okay, so one training time is coming from like large number of environments.
Okay.
Second, if my training time for each environment is very high, that mainly is coming from because I need to compute neural network gradients, Laplacian, which adds to the time.
Okay.
Yeah, and then if you have this progressive learning, it further adds to the time because you first train your neural network on like easier problem, then you take it toward the harder problem. So you gradually change speed around obstacles over time. So it adds to your training epoch. So I think one, the problem itself is bringing the computational cost. Second, the PDE solving their gradients is adding to the computational time. And then these progressive training strategies that we have to use to better guide them to correct local minima is adding to the time.
Okay. Thank you.
Yeah.
So Siddharth.
So so I think we are pretty much on time, I would say. So I'd like to thank Professor Ahmed for your time as well as sharing your research and spending your time today with us for this 1 hour. And I'm pretty sure it was very informative, and I hope to use many of this even in my research down the line. So thank you.
Thank you very much for having me, and thank you, Ameya, for hosting it.
Thanks, Ahmed, for coming and for your time and giving such a wonderful talk. Yeah.
Okay, thank you.
Thank you. Bye.
I will sign out. Thank you. Bye.